Ya, ¿la comparto?
Es que tú no eres anfitrión todavía.
Sí, yes, I am. O sea, I can.
You can.
Yes. I do it now.
Okay. 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 Perfect.
Super.
Okay. Shall we start?
Hmm?
Yes.
As you want.
Yes.
Wait a minute. Yes, wait a minute. Yeah.
Okay.
Yeah. Thank you. Copy. Okay. Super. Yes, I'm ready.
Okay. Okay, so I don't know if we have to wait, Enrique, or in order to start, or we can start now.
Maybe we can start now, or just 2 minutes.
I can adapt the time.
Hmm?
I can adapt the time. Of the
Okay.
presentation.
Okay.
Maybe
So,
we can wait just some minutes.
Okay, Carlos. So we start when you tell us to start.
Yeah.
Yes.
Axel, you have changed the title of your talk?
Yeah.
Okay.
as always.
Okay, I see.
Yes. The main motivation to advance is to present.
Okay. Buenos días, Jaime.
Hola, buenos días. Good morning and good evening for the people in Europe.
Here, Enrique.
Super.
Okay.
So we can
So
go.
let us start. Let us start. First of all, I would like to thank the organizers for to make possible this conference in honor of Enrique. And also would like to thank Enrique for your scientific contribution in the many fields of applied mathematics, and also for transmitting your knowledge to scientific community and for the students, for the young students especially. And happy birthday to you, and I'm happy to be here. It's I know you since for many years, and I remember very well your birthday. It was, in fact, it was my PhD thesis. You were in the jury of my PhD, and it was the day of your birthday. So happy birthday to you. So let's start. Let's start with the first conference of today. It is a pleasure for me to present Axel Osses from Chile. Axel Osses is a specialist of control and inverse problem for PDEs. And now, today, he will speak on two inverse problems in biomedicine, lightsheet fluorescence, microscopy, and MRI obstacle detection. So please, Axel, go ahead.
Thank you, Anna. It's an honor to be here. I share completely the same feeling as Anna. It's the same, exactly, maybe the same story. During my PhD thesis, I met Enrique, and I did a small to advance here presentation of that. For these unforgettable memories in the 90s. I was in France in the 90s studying control theory. Then after that in Chile, I moved to inverse problems, okay? But at the beginning was control. And I remember when my first encounter with Enrique Zuazua at the EHP Institute in Paris. He was smoking in his office. And I came with an idea of rotating multipliers to his office. There was a lot of fog in the office. And he said me, okay, please explain me that and go to the blackboard. Okay. So in 15 minutes, I explained the idea, and he was completely open to discuss, and he invited me after that to Madrid. It was the last year of my PhD. A little bit crazy since just 1 month before my daughter's born in Paris. And then I met Carlos Castro, Sorin Miku, Luz de Teresa. Luz de Teresa taught me about Jaime Ortega, the existence and uniqueness of Jaime Ortega, who did a parallel career to me, so it's really amazing. And also I visited some museums I remember in Madrid, as the Museum of Paul Klee. And then also Enrique accepted to be in my PhD thesis, as Anna is the same case. So many thanks for your support all these years. All this organization of congresses between inverse problems community and controllability community in Chile were very important for us, for our development. And I remember your quick travels to Chile. Once you were just 1 weekend in Chile, I remember. You did a talk and then you lived the country. So it was really, really crazy. Thank you for all that. In general, for supporting Math Blossom everywhere. And there's no anniversary without a gift. So this is a gift for you. Draw for your anniversary.
So who has drawn this?
Myself.
Oh, I mean, that's I didn't know this dimension. Thank you.
Yeah,
Axel.
it's another dimension.
Yeah,
it's a pandemic. It's a pandemic corollary.
The pandemic dimension. Yeah, that's great. Thank you. Yeah. I remember this last workshop you mentioned. Yeah, unfortunately it was very quick travel, but I was also in CMM, and as usual, it was so nice and useful. Yeah. By the way, you said that I was smoking in my office, so of course, when you say it, it's certainly true. But I remember also when I was a PhD student, I think Carlos also used to smoke in the office. No,
yeah,
Carlos.
Years
he was, yeah. And at that time it was common, right, that people will smoke in offices. Yeah. Now it sounds like it's impossible to. But at that time, it was almost advisable to do it, in the sense that this will probably enhance mathematical inspiration.
Yeah, exactly. The atmosphere was unforgettable.
Yeah.
Like coffee, huh?
And coffee, yes. Okay. So I start with the first part of my talk. I will not enter in the details of proofs, since to be honest, I don't remember very well the proofs are very technical in general, but I wanted to just to the point that how these controllability techniques I learned during my PhD and my first years of career were very useful to attack another type of problems, inverse problems, and in particular in medical applications. And one of them is lightsheet fluorescence microscopy. It's a problem that arises from the Faculty of Medicine in Chile. They have a microscope, and they say us to do a mathematical model, or to try to build a mathematical model for this technique. And then another problems arise naturally. So we arrived to the backward uniqueness of the heat equation, for instance, was really non-expected at all. And the other subject I will present if I have time, if not, it's not serious, is about obstacle detection, okay? So lightsheet microscopy is a technique where you have a probe sample and you try to observe this probe is not completely opaque, is semi-transparent in general. So you pass a laser by the object and you try to observe the object slice by a slice. So there's a camera. So there are two steps or two stages. One is the excitation or illumination of the probe, and the other stage is the detection of the object. But there's another thing, there's a material that is fluorescent, and the idea is that the laser excites this material, and then the laser is off, and you can see the fluorescence, the marked cells by a fluorescence chemist, or you can observe this. I will explain this here. This is a typical image you can see, and you can illuminate the probe from the left or from the right. And then what they do, they just merge both images, one side by side, and try to compose an image. But there's a problem at the center, since there's a lot of blur and there's a lot of artifacts. And this is mainly due to the diffusion of the media, the light diffusion or the fluorescence diffusion. So the idea was to build a mathematical model for this technique. And what we did is just describe mathematically these two stages, the stage of excitation of the laser and the stage of how the camera captures this fluorescence light that is excited by the laser. So in general, here some notations. We say that H is the height of the laser, S is the dip, the laser dip, X, Y are the main reference here, and X, H is the entry point of the laser to the probe. So this circle represents the probe, represents the organism you are seeing that has some boundary. Okay, not typically not circular, but okay, it's just a diagram. So from the mathematical point of view, the first stage, the illuminating stage, is modeled by an equation that is called the Fermi pencil beam equation, that is typically used for lasers. And it's just a diffusion equation, a transport diffusion equation, or relative transfer equation that is approximated by a sort of Laplacian in the angle, okay? So it's supposed that the laser is spreading in some way, and when you compute the exact solution, what you have is that the laser is indicated here in the figure, behave as a vertical Gaussian. So if you cut the profile of the laser in a vertical line, you see a sort of Gaussian that depends on the dip and on the attenuation of the media. This is very important, on the diffusion of the media. Here is the diffusion coefficient. I mark it in red, okay? And also you have the attenuation of the media. And this diffusion of the media influences the standard deviation of this Gaussian. Okay, so in general, if you model what is the the quantity of material that is activated, the fluorescent material, it depends also in the concentration of fluorophores, the concentration of the material that is fluorescent. And this is the main source you want to recover. If you can recover this mu, which is the concentration of fluorophores, then you solve the inverse problem. And what are the measurements? The measurements are in the second stage, what is measured by the camera. And the camera, also in the vertical direction, we use a radiative transfer equation model to say, okay, it's light as is propagating in the vertical direction from the fluorophore to the camera. And then there's some integral operators, and we consider also some attenuation of the fluorescent material. So at the end, it's a long formula, but it's very simple. It's a linear model. You have some measurements at some depth and height that depends on the fluorescence concentration, also at the depth and height. So this formula depends on the main diffusion of the media for the laser diffusion. Since alpha is finally a function of is here. Alpha is a function of the diffusion of the laser. So the inverse problem is to recover mu from P, essentially. So we can see this function as a sort of integral with some exponential or Gaussian weight of the source. Okay, and this is the link with the heat equation. After that, yeah, since the kernel of the heat equation is a Gaussian. Okay. And nu will be a sort of initial condition. So here's some numerical simulations to have some intuition on the problem. The idea is that you have a concentration of fluorophores or density of fluorophores that is unknown, and then you can pass a laser, and the laser is illuminating just one slide. This is the 2D version. And the camera received some signal that it's exactly this concentration where the laser passed. Okay, so this is the main idea. So you have a measurement of the camera for each height. You can scan this probe and have a lot of measurements, and then you try to recover the density of fluorophores. Okay. So mathematically, of course, the two important problems are uniqueness and stability of this inverse problem. Uniqueness was already an interesting problem since we found the connection with the heat equation, and stability is more involved. And we arrived to some Lipschitz stability. Was really unexpected. The first guess was a logarithmic stability for this problem, but we have some Lipschitz stability. So what is the connection with the heat equation? As I said before, you can see this operator as sort of integral operator with some Gaussian kernel. And if you change variables, or if you say, okay, all this that is here, including this exponential here, or this quantity is just an unknown function f, okay? And then all this also standard deviation is just sigma 1 that depends on y, which is the vertical variable. And then when you see that, and you see, okay, the inverse problems, you can rewrite it as saying, okay, I have measurements of G and I want to find F, okay? And this is exactly a problem of finding the initial condition, okay, in the heat equation, but there's a little a particularity in this case. And the particularity is that it's not exactly, the measurements are not exactly, for instance, the temperature at some given time, but it's the measurement corresponds to measurements of the heat equation at some curve. So the mathematical problem at the end is to recover the initial condition of the heat equation, knowing the temperature over a curve. Okay, so you know the temperature here, the curve that touch the horizontal axis, and you want to recover the initial temperature. Okay, so it's a little bit different to in other applications. Typically, you know the temperature at some time, for instance, and you try to go back in time to recover the initial condition. Okay, in this case, you know the temperature in a profile, the profile of the temperature. So the main problem was that, so was to attack this problem from measurements in the spatio-temporal curve. Here, I put just in red all related with measurements, and in yellow all what that is related to sources, to unknowns. So the inverse problem is from knowledge on the curve, recover something at time 0. Okay. And then what we prove first in a first paper in inverse problems in 2020, we proved the uniqueness of this backward heat equation problem, inverse problem, and this uniqueness implies the uniqueness of the light sheet fluorescence microscopy problem. So uniqueness in the sense that the fluorescence concentration of fluorophores are unique given the measurements. Okay, so I will not enter in detail in this part. I just say that in a second paper that appeared this year in SciAm, Mathematical Analysis, we proved the stability, and stability was okay if the measurements are small, then okay, the initial condition is also small in some topologies. Okay, so the main step to prove that this Lipschitz stability passed by considering just one sign of the initial condition. We suppose that the initial condition is non-negative, and then we prove a first Lipschitz stability, and it's very important this sign assumption to prove the Lipschitz stability. And then using the decomposition, the sign decomposition of the initial condition, we can do a sort of projection of from the initial condition we go to the solution of the heat equation, and also we consider the operator where from the initial condition we project over the negative part. And using some, I will not enter in the details since the time is bounded. We use some unique compactness argument to prove the stability estimate. So it's not constructive, if you want method to prove the stability. And we were inspired in some paper of Chervova and Oksan. And this implies at the end in our application, the result is interesting by itself, but in our case, it implies some stability for the light sheet fluorescence microscopy problem also. Okay, and we need some technical hypotheses related to the regularity of this fluorophore concentration, and in terms also of some location of the fluorophores away from the boundary. And I will skip, I think, the proof of this, but just the idea in this figure to prove it's interesting things since we translate the problem of knowing the temperature over a curve, try to recover the initial condition into a different problem in a non-bounded domain. That is, if we know the temperature at some some curve, then we know, in some sense, the temperature in some domain with a bounded complement. Okay, but it's typically also in control of the heat equation in non-bounded domains. Okay, so the observation region or the control region is with bounded complement in this case. And this is the main idea. And to do this, what we did, we introduced some sort of energy that is just integral of the solution over horizontal lines from the curve to the infinity. And by integrate this energy and by doing some estimations, we can estimate the size of the source from the size of the solution over this unbounded domain with bounded complement and conclude the stability. Just if you want more details, please see or I can send you the paper. And I wanted to say just here, since we cite also some works and one work of Enrique, we can also prove logarithmic stabilities with less assumptions over the support of the initial condition, and it passed by Kahneman inequalities and etc. This is typical in the backward heat equation type problems. Okay, and in this case you have logarithmic stability, what is worst, but okay, we also did that in the article to have another view of the same problem. And we also did some numerics. For instance, here you have the original problem where you just merge both images, and also you have in the center line here in the center axis of symmetry, the vertical one, you have here the profile, and you can recover something which is very smooth. Okay, but if you use the model and you use techniques for solving the linear problem or the minimization problem using this functional, this model, mathematical model, you arrive to something which is much more detailed in this part. That is the problem in practical microscopy. Okay. Also for the stability, we studied numerical stability to see if numerically this Lipschitz stability exists, and it was the case. So we construct some simulated probes trying to mimic what you see in the laboratory, and prove that depending on the amount of illumination you have, you can go farther and farther in this case, the exact solution is in green, and you arrive with more and more illuminations, okay, to obtain the uniqueness of the solution. Okay. Of course, if you illuminate just one side, it's not okay, but both sides is okay. This is the final theorem. Okay, the second part, I will go. I think I have maybe 3 minutes, but just to mention stability, we also attack this problem, which is a problem coming from, just to mention it, coming from also from medicine. And the idea is to recover the shape of the valves in the heart from velocity measurements, and velocity measurements that you can obtain from MRI measurements. So with MRI, you know, MRI, magnetic resonance imaging, you can also find not only concentrations, but not only densities, but you can also find velocities, the velocity of blood. And if you have the velocity, the idea is to use this velocity to find something in the fluid. In this case, the idea is to find obstacles. The valve is you can see the valve as an obstacle. And the main idea, without entering details, is that you replace the obstacle, in this case, the valve that is here at the left-hand side, by a resistance. This is the main idea. You replace the value by a resistance, so a coefficient in the equation. You get away the value and you put a coefficient in the equation. And the main idea is to change the inverse problem. The inverse problem is to find the shape of the valves from the velocity measurements, local velocity measurements. And the idea is to change these inverse problems by finding the support of this resistance from velocity measurements. So mathematically, it corresponds to change. You have a geometrical inverse problem where you want to recover the shape of the valve, which is here denoted gamma W, from velocity measurements, by another problem, equivalent problem, where you have now a coefficient gamma in the equation that is a resistance coefficient, or the reciprocal of the permeability, if you want. And the idea is to recover gamma instead of the little gamma, instead of the boundary, okay, capital gamma. And you can prove the convergence, so you can prove that these two problems are very related if the gamma tends to infinity in the regions where you have obstacles, okay? So if the resistance is very high in these regions. And you can prove uniqueness using the Fabre-Lebeau result about unique continuation for the Stokes system. And you can also prove, using Carliman inequalities, you can also prove stability. Okay, stability, and the stability is logarithmic at the end. And it shows that you have to measure not only velocity, but you have to measure also the curl of the velocity. Okay, so the right functional to minimize is velocity plus the curl of the velocity. Okay, but it's a very difficult problem. You have some geometrical abstractions regarding the weight, the Kaleman weight function. And we have also some numerical results here. Here, for instance, we have in the first column, we have the real values and the recovered profiles in red or in pink. And here you have the iteration of the method. The second column is how you found the step by step, how you retrieve this sort of resistance coefficient. And the boundary of the resistance coefficient is exactly the boundary of the valve. Okay, so this is the main idea of the problem. This is done by using dolphin adjoint. And we also have some simulations how to recover, for instance, objects in fluids using velocity. In particular, we were very interested in how to recover objects that are not smooth. For instance, here you have a circle. You have a coefficient that the support is a circle but smooth, and this is okay. But what happens if the object is not so smooth, since it's very challenging from the numerical point of view? And we try to recover the shape of the object by observing the velocity on this square, okay, here. So this is the exact solution, and these are the iterations to recover the shape of the object. Okay, I advance in time, and you have this. And to do this, we need to, at each iteration, we need to reshape or to adapt locally the mesh in order to obtain good results in this case, for instance. So you can apply another type of method. For instance, there's a method that is called the spectral adaptative also method, that consists in choosing the spectral basis, but adapt this spectral basis to the shape of the object. Okay, this is the work of Maya de Juan. Okay, I think I finished. There's some references here, but I want to respect time. So thank you very much.
Okay, Axel, thank you very much for this excellent talk. I don't know if there are any questions or comments. Please, you can use your microphone or write in the chat. Jaime?
Yeah, so can I ask something?
Yes, Enrique.
Can you
please.
hear me now? Yeah, I'm sorry that early I had some difficulties to join in Zoom and then with the micro, but now I think everything is working well. So
Yes.
Axel, in the problem of the heat equation that you wrote, the inversion of the heat equation, you said that you have several inequalities, in particular the last logarithmic inequalities. Can you show that slide again?
Yeah. Sorry, I have to
go backwards.
Go one by one, but I will arrive. Yes.
Okay, so here, for instance, right?
Yeah.
So here, this is the heat equation, right? And you recover U0.
Yeah.
Out of U localized in a subdomain, omega.
Yes.
With bounded complement, okay? So
Yeah.
it's like the stereo of a disk or something like this, right?
Exactly.
And then you say that you can recover the solution backwards, but for this you need some, yeah, I see, some
Yes.
upper bound on U0 in some, is kind of an interpolation inequality, right?
Yeah.
Yeah. Okay, I see. Mm.
Yeah.
Yeah, now, and then you mentioned also numerical simulations. My question is, so normally for the heat equation, these kind of inequalities, which are related to the quantitative version of the backward uniqueness,
yeah.
Okay, you can prove them for any time interval, right? 0 capital T, right? You agree, right? So this inequality is true for any time horizon, capital T, right? Okay, so yeah, there is no restriction on capital T on your statement. But then when you are doing numerics, of course, when the time horizon is longer, capital T is larger, it's harder and harder numerically to recover U0 because, the problem is exponentially ill-posed, right?
Yeah.
Did you work on this? I mean, what is your experience with that? Did you really succeed? Because many of the existing methods for recovering the initial datum, they work for short time. I mean, numerically, right? Numerically, they work for short time intervals, capital T, but when you try them in longer time intervals, they fail, right?
Yeah.
And actually, this problem is very similar to the one that people in image processing encounter when they do deconvolution, right? They can do deconvolution provided the convoluting kernel, is moderate, right?
Yeah.
Mm-hmm.
Yeah. In general, we were in fact the main criticism for the paper was that they say it's really useful. It's really in practice, no? This algorithm to the microscopy for microscopy images, since you have logarithmic or you have this ill-posed nature of the problem. And in fact, when you have the measurement from the camera, for each line, for each vertical line, you have to solve a sort of initial backward heat equation problem. Okay, but surprisingly, even in the presence of noise, okay, the results were okay. We solved this problem by just solving a linear problem. Since you have a linear system of equations and you can invert this system, and the results were very good in terms of robustness with respect to noise, and also the camera is near the object. Okay, so I should say that the signal arrives to the camera. I should say T is small. Okay, so you arrive with a very good signal, of the temperature you want at the camera. You are very near to the object. So I think this is the first reason. And the second reason, we prove elliptic stability, which is much better than the logarithmic stability, by supposing that the support of the source is bounded. And we were surprised. We tried to find a mistake somewhere in the proof and trying to see how this happened. And we're working on this on more detail with numerical simulation, etc. But for the moment, the only explanation is that there's an assumption that the support of the initial condition, in this case, the support of the object is bounded for each line. Okay, but okay, I don't have maybe a convincing answer, but it's a very interesting problem.
Definitely.
It works numerically.
Thank you, Axel.
Thank you, Enrique.
So in which paper is the numerics of this written? In which of your papers?
In the first one, that's the direct model, and we solved the inverse problem with a linear system. And in the second paper, in the science paper, there's more details about the stability, numerics and stability. This, for instance, these figures are from the second one.
Okay. Thank you, Al.
Thank you,
Thank
Axel.
you.
Jaime, please.
Hi, Axel. How are you? Nice to see
Hi,
you.
Jaime.
One thing for the object detection, you are using level set or something like that, or you are just using a parametrization of the sphere or something like that.
For the second problem?
Yes, for the object detection.
For the object detection, what we do is here, for instance, what we do typically I will show you the simulation. Once we in this case, the number of parameters are infinite. You know, are all the infinite elements should be the degrees of freedom of the function here, of the mesh. So you have a lot of parameters, but at the end, what we do, we just cut horizontally this function, and we find local maxima. Okay, and by marking this point, we then construct just a line connecting this maxima, local maxima. So it's very simple. But I agree with you, maybe with using some splines, some more soft
because maybe one approximation with level set can help you also.
Yeah, I agree. Yeah.
This is the work of your student Jorge.
Yes, also Antonio Leitao worked on this type of method.
Very good.
Yes.
Okay.
Yes, but I agree. You can reduce the number of the degrees of freedom of the problem.
No, but
the idea here is to not. We don't have really the valves. The domain don't have the valves. So the idea is to remove the object and just put a coefficient in the equation. This is the main simplification.
Okay. Perfect. Very nice. Thanks.
Thanks. And thanks for all your work on this subject also. I know you are a specialist. We copy us, always.
I hope it could be useful.
Yes.
More question or comment from the audience? Probably, Axel, I can ask you a question. And what about the random noise in the numerical algorithm for the reconstruction of
the second one?
Yes, the second one. Yes.
Yes, I don't have a simulation, but MRI resolution is very bad. In general, you have big squares and a lot of noise. And we tried with this by simulating MRI. not with real data, but with simulating MRI, and we succeed to have good estimation. But instead of going to real data in 2D, since we write the paper in 2D, our student is now in Groningen in Netherlands and is trying to build a model in 3D with a valve in 3D with three parts. It's very complicated in 3D. And the idea is to use the model in 3D with real data in 3D, trying to put all together. But step by step, we think it's a very good approach.
Mm-hmm.
It's a very good approach since you remove the valve and you replace just by a coefficient, and it's more easy recover a potential than a boundary.
Okay, so thank you very much.
Thank you, Anna.
Okay, if there are no
Gracias, Axel.
gracias. So we can pass to the next speaker. Thank you, Axel. Zhang.
Hi, everybody.
Hi.
Hello, Rick.
Hello.
Hello, everybody.
Hello, Shu.
Hello, Rick.
Hello, Shu. How are you?
Fine, and you? So,
Very good, very good. Yeah.
Yeah,
So
I'm
despite
very
all difficulties, we are still all good. Yeah.
oh, yeah, everything's great.
So you are in Sichuan?
Yeah, I'm at home, in fact.
Oh, good, good. Okay,
Yeah.
but you even at home you have many mathematics books, right?
Oh, yeah, right. Yeah,
Okay, good. Yeah. Is to feel
Yeah.
safe, huh? Yeah.
Yeah,
Okay.
yeah.
Yeah. And how is life in Sichuan now? Can you
Now it is,
walk to office and everything, or?
Yeah, we can go to office, in fact. Yeah.
Okay.
We can go to office almost every day.
Mm-hmm.
Yeah.
Good.
So now it is about 9 o'clock in the evening. Yeah.
Oh, it's too late for you. Yeah. Okay.
Yeah,
So then
but
you
it's
should
not
give
too
that
much,
the
not
talk
too much,
before
in
you
fact.
sleep,
Yeah.
right? So
Yeah. So this is why maybe I cannot attend
yeah,
these
the end of the
lectures.
series. Yeah,
Yeah.
definitely.
Yeah.
Okay.
Because the difference
Nice to
is
see you,
11
Shu.
hours.
Yes.
Yeah.
Very nice to see you. Very nice to see
Yeah,
you.
me too. Yeah. And so
Yeah. Okay.
to see, yeah, many people else here. Yeah.
So Professor, can you try to share your screen, please?
Sure. Just one moment.
Okay.
So I think I will have to. Oh, just a moment. I think I should. It's okay.
We can't see. Okay.
It's fine.
Yes. Yes. Now we can
Yeah.
see.
Great.
We can see your slides.
Great.
Okay.
Yeah.
Okay. Are you ready?
Yeah. I'm ready. So.
Okay. So. Thank you very much. Let me introduce you. So we have now Professor Zhang. He is a specialist on control and also stochastic differential equation, control partial differential equation, and also stochastic differential equation. So he will speak about operator valued backwards stochastic Riccati equation and application. So please, as you want.
Okay, thank you, Anna. So thank you for your introduction. So I would like to thank the organizer to invite me to give this talk. In fact, it's my great pleasure to attend this workshop in honor of Enrique for his 60th birthday. So you know, I know Enrique almost 30 years ago. That is about 1994, when I began my study of PhD thesis. So, and in fact, I met Enrique in a conference in 1998. After that, we have many discussions, collaborations, particularly. So when I starting from 2000, I went to Spain to study with Enrique. In fact, Enrique is my standard mentor for many years. And also after that, in fact, he's also my beneficial friend up to now, in fact. So you know, I worked with Enrique in Spain, first at Universidad de Chile, then at Autónoma, and stay there, stay in Spain for more than six years. After that, I returned to China, and that is not, in fact, after that, we keep the collaboration with Enrique, not only between us, but also continued in my student like Chindu. On the other hand, even when I returned to China, Enrique, as before, gave me many advice, encouragement, and comments for the work. And this helped me a lot. In fact, the talk of today is more about stochastic PD control. So at the very beginning, when I started this field, Enrique gave me many encouragement. And I would like to thank him for very much for his long-standing support, encouragement, and advice, of course. Yeah. Okay, so this talk is based on the following two papers. The first one is for stochastic OD problem, and the second one is about the optic feedback control for stochastic LQ problems in infinite dimensions. In fact, for more reference, so I would like to mention this book. It is published in this year, and this is something like an introduction to the field of control of stochastic PDEs. Okay. So the outline of my talk is as follows. So first, I will give you some introduction, especially some motivation of our talk. Then I will review the classic LQ problems in the dynamic stage. Then I will talk about some result for stochastic LQ problem in infinite dimensions. So finally, is the same problem but for infinite dimensions. So in fact, the simplest Riccati equation is like this one. So dot x equal to x squared, and this equation can be solved explicitly like so xt is equal to this one, and this equation, this solution blows up at this time t is equal to x0 to the power -1. So this is a very simple result. This very simple equation, in fact, dates back to the very early period of mathematics. In fact, this equation was related to many big names in the history of mathematics. For example, Bernoulli and Riccati, and also Euler and Zhang, Dalam, and so on. Okay. So in fact, the term Riccati equation is used to a broad sense later. For example, this equation also appear in many different fields, such as boundary value problems, scattering theory, and so on. Particularly in the second half of 20th century, the different matrix Riccati equation theory was brought in the science and engineering. This is particularly because of the seminal work by Karman, who used matrix-valued Riccati equation to solve some control problems, such as linear optimal control and filtering problems with quadratic functions and so on. So in this work, so we will introduce operator-valued backward stochastic Riccati equation for general stochastic linear quadratic control problems spanned in infinite dimensions. Okay, so to do this, let us review the classical result. So given capital T, we consider this a very simple control system. So it is dot x to a xt plus bt u. So this is a linear control system in infinite dimensions in the deterministic set with a constant functional. This is a quadratic functional like this one. So here Q, R, and G is symmetric matrix. Okay, so our problem is minimize this quadratic functional over the L2 space. So if there exists U bar which minimize this functional, then we call this problem is solved. And this U bar is an optimal control, and the corresponding state X bar is equal to the optimal state trajectory. So our problem is how to identify U bar. So in fact, this is very simple. It's quite classic. We use the classic variation law. So for any epsilon and U belongs to this L2 space, we write U epsilon is equal to U bar plus epsilon UE, epsilon U, and the X epsilon is the corresponding solution. So then X epsilon equal to X bar plus epsilon R. Here R solves this variation equation. This is because we consider only the linear problem. Okay, so this R dot is equal to AT RT plus BT UT. So this is a variational equation. Okay, so then we can compute what is J of X epsilon. It can be computed explicitly in this way. So this is a third order term, this is the first order term, and this is the higher order term. Okay, so then we get this first order necessary condition about this X bar and U bar. But this first order necessary condition does not look fine. So we will need to rewrite it as follows. So we introduce a backward ODE. So psi dot is equal to this guy, and with psi cap t is equal to this one. Then by duality between these two equations. So this is equation 5, and also this backward ODE. So then we get this variational identity like this one. Okay, so then we can, so finally we can get this optimal control, which is U bar t is equal to RT minus 1 times BT times psi t. Okay, this is perfect. This looks very good. So we can, in some sense, we can find this U bar in explicit way. However, this optimal control given by line, this guy is not a feedback form. It's not a feedback form. So in control theory, of course, it is well known that we hope to find the feedback control. So to do this, formally, we assume that this psi is the solution to this guy, this equation 7. So we assume this psi is equal to some pt times x bar t. So then combine 9 and 10. We obtain that this u bar t is equal to rt minus 1 times pt prime times pt x bar. So this means that whenever we find this capital P, so we get feedback control. So the problem is how to obtain this capital P. Okay, so to do this, we differentiate this equation set is to pt times x bar t. So then we can get this equation. I forgot this equation. We just compare the first one and the last one. So then we get we have to choose this capital P satisfy this Riccati equation, which means that we need to assume that this dot P is equal to minus pt times at minus at pt plus this guy minus qt, and the final data is equal to capital G. Okay, so this means that if we can find this capital P, so then we obtain the feedback control. So in fact, we have this well-known classic result. So this means under some assumptions on the capital R, here in fact is if capital R is uniform positive. So then for any integer x0, the RQ problem is uniquely solvable. If and only if the Riccati equation, so this nonlinear Riccati equation admits a uniquely solution, capital P belongs to this space. Here we have to have to be careful because this equation, this is Riccati equation 12 is a nonlinear equation. So generally, because of its nonlinear rate, the global solution is the global solvability is not guaranteed. However, this equation comes from the RQ problems. So here this theorem says that if the RQ problem is solvable, then this Riccati equation is also globally solvable. Okay. However, we will see a completely different phenomena in the stochastic set. In the stochastic, we will see this. We have to reformulation the problems. Okay. So now let us see the stochastic set. Okay. We first consider the finite dimensions. So it is the stochastic RQ problems. Okay. So this is omega f, capital F, P is a complete filtered probability space. And this capital F is a filtration, And here we assume this is a natural filtration generated by a one-dimensional Brownian motion, W. Okay. For any n and m and the unit delta s and eta, we consider this controlled equation. So here, the equation is very simple. It's a linear equation. So dx is equal to ar x plus b UDR. This is a drift term. And the diffusion term, so because in the stochastic, we have the main difference is we have a diffusion term, this guy, which is related to the Ito's integral. So plus CR XR plus DRUR DWR. So this we have this extra diffusion term. With the quadratic cast function, this is a quadratic functional. This is more or less the same as before, except that we have to take expectation. Okay. In the above, so UT is in this L2 space. So this space, it is a space of admissible controls, and X is a state variable. So our problem is almost can be posed as before. So we hope to find U bar which minimizes cast function. This is a problem. So this is a stochastic LQ problem in finite dimensions. Similar to the deterministic set, Riccati equation and their variants are fundamental to study SLQs. However, in the stochastic set, we have to consider backward stochastic Riccati equation. For example, for our problems, the desired backward stochastic Riccati equation takes a following form. So it is dp is equal to. So this part is more or less the same as before. However, we have an extra term plus lambda dw. So we have an extra term. This is the martingale term or diffusion term plus lambda dwt. And also this is some difference about the nonlinear term. So this is a nonlinear term. So nonlinear term, we have this k. This is the more perilous pseudo inverse. This term is very similar as before, plus r. This capital K is r plus d p d. But we have also this capital L. This capital L we have if it is quadratic with both capital P and also with this capital lambda. So this is much more complicated nonlinear problems. Okay. This equation, in fact, in a very much simpler form, was introduced first by Unham in 1968. In the early works on SLQs, the coefficients A, B, C, D, R, and G assumed to be deterministic. In this case, the Riccati equation, this equation, in fact, if all of the coefficient is deterministic, then this equation is also a deterministic one. In fact, in this case, lambda equal to 0, equal to 0. Okay, this is more or less, in some sense, this is a simple case, but still there are some difficult problems, even this simple case. It was Bismuth who introduced, it is the first work that addressed the study of SLQs with random coefficients. So in fact, this equation 16, so this equation 16 was first introduced by Bismuth, but at the time, this equation is only introduced formally. And also at that time, only some very special and simple cases can be solved. Okay. In 1992, Penn proves the well-positiveness of the equation 19 under the condition that this capital D equal to 0, which means that there is no control in the diffusion term. Okay. Okay. The general case that is in the finite dimension, which the condition capital D equal to this extra term was dropped in 2003, in which it was proved that this equation, so 16, admits a unique solution in a suitable space under the assumption that Q, G, and R are positive or uniform positive. So we mentioned before that in the deterministic case, the purpose to introduce Riccati equations is to design feedback control. So more precisely, under some assumptions, so one can show the unique solvability of recursive problems is equivalent to that of the corresponding Riccati equations, and by which so one can construct the optimal feedback control. But the same problem is only partially well understood in the stochastic set, such as the case that all the coefficients are deterministic, or the case that the diffusion term is time-free, which means that capital D is equal to 0. However, for a general case, that is, if we don't have this assumption D equal to 0, so then the solution P lambda to 16 found in the work of time is not regular enough to serve as the design of the feedback control. Okay. So because of this, it is quite natural to ask such a question. So is it possible to link the existence of feedback control rather than the solvability for stochastic recursive problem directly to the solvability of the Riccati equation? So this is the main purpose of our work. So we will give an affirmative answer to this equation. So in fact, so we call a process theta is an optic feedback operator for problem F is Q if for any initial data is eta and control, we have this so the coefficient the functional with this optic feedback operator is this means that this theta is an optimal control. This theta x bar is optimal control. So in this case, so we call our problem has a feedback operator. Okay. So our main result is as follows. So we can prove this one. So our problem F is RQ admits a unique optimal feedback operator rather than uniquely solvability. So this operator theta belongs to this air infinity space. If and only if the Riccati equation, this is a backward Riccati equation, stochastic backward Riccati equation, admits a unique, this global solution P lambda in this space, such that this capital K is uniform positive, and therefore, and such that the feedback control, the optimal feedback operator theta is given by theta is equal to capital K minus 1 times air. So this is our main result. For some special example, so we can prove that there does exist a feedback operator theta. Well, for another situation, one can show that the desired feedback operator may not exist. So there is a very interesting problem. That is how to find general conditions to guarantee that our stochastic Riccati equation 60 meets unique solution, so P lambda. In this space, the difficulty is here, we need this lambda belongs to infinity. This is, in my opinion, this is a very difficult problem. Of course, it is unsolved. So in fact, one can construct a counterexample which shows that a solvable problem F is a Q, which is solvable, but it does not need to have feedback controls. This is a significant difference between SRQs and their deterministic counterpart. In fact, as we reviewed before, so one can always find the desired feedback control through the corresponding Riccati equation whenever the RQ problem is uniquely solvable. Okay, so this is a main difference. It is in fact a completely new phenomenon in the stochastic set. Okay, so now we will return to the infinite dimensions. This is the same for RQ, but in infinite dimensions. So we need this Hn and the capital U are separable Hilbert space, and A generates a C0 semigroup. So we can formulate a problem very similar in the field dimensions. So for initial data S eta, so we consider this controlled linear stochastic evolution equation dxt is equal to A plus A1 times xt plus BUT. So it's the drifter, and also we have the diffusion terms CXT plus DUT times DWT. Okay. This DW as before is one-dimensional Brownian motion. Okay. With these quadratic castle functions, this is also, and also we can these coefficients. So A1, B, C, D, and Q are suitable operate via the stochastic processes, and also. So now, very similar as before, we can formulate our object control problems. So our problem is for each initial data S eta, we hope to find U bar which minimize this functional. This function is quadratic function. Okay, the functional is like this one. Okay. So for our problem SRQ, because of our work in field dimensions, we introduce the notion of optimal feedback operator as follows. Okay, so an operator theta belongs to this very strange space. By the way, I don't have time to explain you. It is a suitable operator, stochastic operator. It's called optimal feedback operator for problem SRQ if this inequality hold for any data and control U. Here theta as before, theta x bar is is in fact the optimal control. Okay. So also we introduce the operate value backward stochastic Riccati equation. So this is our Riccati equation. This equation looks very similar as before, but the main difficulty is this lambda is an operate valued process. Okay. So in fact, this is the new essential difficulty in the start of this equation. Okay. So in fact, when the dimension of H is infinite, indeed in the this infinite dimension setting, so although LH is a space of linear bounded operators from H to itself, this space in the usual topology is still a Banach space. Unfortunately, it is neither reflexive nor separable. Even if H itself is a Hilbert space, is a separable Hilbert space. So in fact, in the previous literature, there exists no such stochastic integration of equation theory in the general Banach spaces that can be employed to treat the well-posedness of this equation. Especially to handle the stochastic integral term lambda dwt. This is my difficulty. Okay. So in fact, I don't have time to explain it. This is related to a long-standing unsolved problem in non-commutative homological analysis. Here, where of course, everyone knows, generally speaking, you want to start the difficult nonlinear PDEs. So PIB need to introduce new concept of a solution. For example, viscosity solutions for HB equations, renormalized solutions for KPZ equations. So here in this work, so we introduce another type of solution, that is transfer solution to our operator value backwards stochastic Riccati equation 24. So even this concept of transfer solution to operator value backwards stochastic Liapoff equation was first introduced in our previous work in 1914, and it was important to study first and second order subsequently for stochastic optimal controls in infinite domains. So here, in fact, this notion is also can be used to our nonlinear problems. So in fact, I will not go to the details, but here we just we need to introduce two forward stochastic evolution equations, so dxi. So here, vi and xi valued in a Hilbert space. This is very important. It is a Hilbert space, but if not rather than LH, the space of operators. Okay, so then so we call P lambda is a transfer solution to our nonlinear equation 24 if the following three conditions. So this is the most important is we need this like transfer solution for PDEs with non-harmonious boundary problem. So we need this this variational inequality holds for any t x1, x2, and u1, u2, v1, v2. Okay, this is our definition of transfer solutions. Okay, so our main theorem is as follows. So suppose that A generates sincere group, but this is a technical assumptions. So this assumption can be dropped in a recent work by Chile and Tianxiaowang. So then our problems SLQ admits optimal control optimal feedback operator theta if and only if our Riccati equation admits transfer solution P and lambda in this sense. In this case, we can really find the optic feedback operator. I think this, I don't have much more time. So I would like to say again, happy birthday, Enrique. So in Chinese, so we hope your 福如东海，寿比南山. So this is something like the English translation. So may your happiness be as immense as the sea, and live as long as the mountains. Okay, thank you for everybody.
Oh, thank you very much, Shu, for this interesting talk. Some questions or comments? One question. Sorry, I don't see who.
I think I will have to start the.
Okay, Alessio.
Yeah.
Okay. Donc, please, Jean-Michel.
Yes, thank you. Thank you, Shu, for this very nice talk. It's a pleasure to see you again.
Me too, Jean-Michel.
In finite dimension, LQ methods are usually used, in fact, to construct feedback laws, which are because they are robust with respect to perturbation. So I was wondering, maybe the key point is to get feedback law. Is it possible to use something different than the LQ for stochastic, maybe just infinite dimension, in order to get feedback, but maybe not coming from LQ, but which may be robust, but for stochastic.
Yeah, right. Yeah, in fact, we hope to find the solution of Riccati equation exactly as you meant to find the feedback control. But unfortunately, in the stochastic set, the Riccati equation is is much more complicated than the dynamic set. So now, even for the finite dimensions, I mean, for stochastic Riccati equation in finite dimensions, so they will pose this of that equation is much less understood.
Sure. But is it possible to use some other, because at the end what we want is to construct a feedback law. Is it possible to use a different framework than LQ to construct feedback law in the case of stochastic linear differential equation in finite dimension? Something different, not LQ.
That is a very interesting question. Yeah, in fact, as far as I know, there's some another way, but still, for example, there is the problems can be reduced to another one. It is a forward-backward equation, but the problem is in many cases that forward-backward stochastic equation it is linear problems, but in some sense these two solutions are equivalent.
Okay.
Two approaches are equivalent. But maybe you are right. Even in the dynamic setting, so it is much easier to understand the Riccati equation itself. But in the stochastic, maybe you are right. I don't think this problem before, but I think it is a very interesting question. So maybe last time when I meet you, I can give you a solution, answer that.
Okay.
Anyway, this is a very interesting question.
Thank you. Thank you.
Yeah.
Thank you.
Okay, thank you, Jean-Michel. Alessio?
Okay, so hi, Sue. Nice to see you. Yeah, my question is very simple. I mean, I've always seen this presentation with a stochastic, I mean, I'm talking about the finite dimensional case. So I've always seen this with this Brownian motion, but I mean, could you have differently some other, say, a Levy process or jump processes in your dynamics, say?
Yeah, that is, so in fact, in our work, we consider the most, I think the simplest case. Yeah, of course, there are many cases, many problems that were not addressed in our work. For example, not only the equation driven by Lewis-Levy process. So in fact, we consider only the case of that the problem is one-dimensional.
Okay.
Yeah, even for this one-dimensional case, so the problem is much less understood, in fact. So of course, I think it is possible to prove some result when the equation is, I mean, the uncertainty is driven by Levy process, or even driven by the general martingale setting. Yeah, I think that is possible. We can address these problems, but so finally, so the problem is how to give the real feedback control. I think this should be even more difficult.
Okay.
Yeah.
Okay. Thank you.
As far as I can imagine.
Okay. Thank you, Axel.
Thank you, Alessio. Enrique, please.
Yes. So, Shu, thank you for the interesting talk. Well, as you know, I know not much about this stochastic context, but oftentimes people exploit the link with diffusion processes, right, to avoid somehow the stochasticity and get into the deterministic setting. Is there an analysis of this kind linking the stochastic Riccati and the deterministic Riccati to the price of moving from finite dimensions into infinite dimensional models?
Pardon, Enrique?
So, I mean, do you agree that one can link finite dimensional stochastic equations with diffusion processes?
Yeah, sure, yeah.
Okay, so then the question will be, how does the Riccati, say, time evolving or a steady Riccati operator, how are they linked in both contexts?
Oh, yeah, Enrique, that is very interesting question problems. So in fact, we have tried to understand the problem for many times. So in fact, in some sense, so this is I think I have wrote some notes, but it is in Chinese, unfortunately. So my understanding is that for the equation problems, so in some sense, diffusion, I mean, stochastic equation can be linked relationally to heat equation, for example. But unfortunately, this is equation. This is a problem of equation. But for control problems, I think the link is not as clear as the equation itself. So which means that for control problems, in some sense, it is something like we hope to control the coefficient of, for example, the heat equation. In some sense, yeah. So there are some things that we hope to understand, but unfortunately, we have not found the real link. But this is a very, very important problem, because in fact, this is in some sense we are considering the same phenomena, diffusion phenomena. There should be one unified theory, I think this is what they hope tell me. Yeah, but the problem is how to unify these two control problems. I mean, which means that the LQ problems for the heat equations and also the LQ problem for stochastic equations. At this moment, what I can say, we hope to find the relationship, but unfortunately, so far, so we don't find the correct relationship, unfortunately.
Yeah, you are right. So actually, there is an analogy also with what happens when you consider ordinary differential equations as the characteristics of the transport equation, right? So now, if you control a classical setting of the AB problem that you introduced in the very beginning and linear finite dimensional, if you think on the ordinary differential equation under control, and then you move into the context of transport equations through the link of solutions of transport equations with characteristics, you see that the control enters as a control on the velocity field of the transport equation. So it becomes a bilinear control, right?
Yeah, sure, yeah.
I think it's the same for the stochastic ODEs and diffusion equations, yes. So to make this link, you have to quit the linear setting and move into a more complex bilinear control context. Yeah.
Sure.
Okay, thank you. All this is very interesting. Yeah. Okay, so I hope we can meet soon in Sichuan and we can discuss all this in person, right?
Sure. I hope also very much.
But it seems the time to travel to China is still not very close, right? So things are not easy, right?
I suppose maybe the next year or at most the year after next year, I believe it is possible.
Okay.
Yeah, which means that 2023 at most, and more 23.
Okay, let's hope.
Yeah, maybe next year. Maybe next year.
Okay.
So also everybody here, Michelle and Anna. So I hope that we can meet in Sichuan in Chengdu next year.
Yes,
that will be a great pleasure.
So
yeah.
Okay, thank you, Shu, and all the best for all friends in Sichuan. Bye, ciao.
Yeah. So very happy. Nick.
So thank you very much, Shu, for your talk. And I think we have no time for more questions. So let's continue.
Okay. Let me start.
Okay.
Can you view the full mode?
Okay, Mahamadi, okay. Nice to meet you. Are you ready? Are you ready?
Yeah, I already shared my screen. Can you see it?
Yes.
Okay.
I can see it correctly. So let's continue. Next speaker, it's a pleasure for me to introduce Mahamadi Warma. He's a specialist on calculus of variations on non-local and fractional PDEs and optimization and controllability. And he will talk about controllability property of fractional PDEs. What is the state of the art? So please go ahead.
Yeah, thank you very much for the nice introduction. And thanks for the organizer, Carlos and Sebastian, for inviting me to give the talk. Because if I'm not mistaken, at least for all those people giving talks, maybe I'm the one who met Enrique the last, because I met Enrique first in 2008 in Puerto Rico. Enrique was always traveling to Puerto Rico before because his wife is from there. But in 2008, before coming, he sent an email to Valentin and me that he's visiting Puerto Rico every year, but he wondered if he can pass to the university and that we can meet each other. It was a very nice pleasure that we started. And since 2008, I see Enrique at least once a year, except last year that everybody knows because of the pandemic. And when I know Enrique at that time, I was still an assistant professor. Then when I met Enrique, I was just listening to him because I was afraid to say, you know, things that, and I also was not doing control theory. But after 3 years, he initiated me to control theory, and we start working on that. And he said, okay, why not write a research proposal to the US agency? That's why you can survive in the US. Because in the US system, you need to have grants, otherwise it's very complicated. And yes, he introduced me to the people that he knows in control theory in the agencies, and we started, and we were successful for getting our first grant. And then from there up to now, we are still having grants from the agencies. And I switched a little bit from semi-group of, okay, everything is PDE, but I do a lot more control in the last years. I met Enrique than the original thing I did in my PhD at the University of Poland. Well, nice, Enrique. Thank you very much for introducing me to this control theory and to the control peoples. For example, Sebastian, I met Sebastian in Bilbao when he was doing a research, study with Enrique. That's where I met Sebastian for the first time. Now let's go a little bit to the math. I want to talk about controllability property of fractional PDE. I could have talked about something else, but I choose this one because it's the main result that I will present here is my last work with Enrique and Umberto. And I can assure you that maybe it's one of the papers that took Enrique a lot of time, because we are already more than 2 years, because every line should be checked, because classical intuition that we have from local PDE for the Laplace operator is no longer easy to see for the fractional one, but the talk will avoid all those things. I will just give you the idea what we have and what we have proved. Then, but first I will just, I know that almost all the audience know control theory, especially for the classical one, but I will take few minutes to recall those things for maybe young generation who are between us and are not in control theory. Then, like, if you take the classical heat equation, that is the classical heat equation, then usually you have two types of control problem that you can do. Then the first one is the interior controllability. Then interior controllability, that is here you have your state U that you want to control. And you have your control function that is F. And this control function is localized in a non-empty open set of the domain omega, where you have your evolution equation. Then another type of control is that you have here, the boundary control. Then in the boundary control, then inside of putting your control in the interior, you are at the boundary in one part of the boundary, and you want to make some partial measurement then from the boundary, and then recover the full information on the system you want to study. Then that is the main purpose of control. Then from a partial measurement at the interior on the boundary, you want to recover the full information on the state you want to control. Then for the, let's see what is. Yeah, for the classical thing, that's what we have here. Then first one has to see what are the set I can reach. Then of course for the interior control, then what you can reach is U of t is the time, and you take F to be your control, that is an L2 function on omega times the time. Then that is the set where you can reach for the interior control. The same for the boundary control, then you have the set of reachable state is all the UT where G, your control is in L2 of omega, a gamma times 0t. But usually, okay, if you consider, finite energy solution for the interior control, there is no problem that taking F in L2, you are sure, for the heat equation to have finite energy solution. But for the boundary control, if you have Dirichlet boundary control, it may happen that G in L2 is not enough to have finite energy solution. Maybe at that time, if you take L2 its value in H1/2, yes, that will work, but it's not a big deal. If it's not, one may consider a very weak solution, or usually solution called solution by transposition. Now, the three notions of controllability are defined that everybody knows, that we say that the system is approximately controllable in time t if the set of restable state is dense in L2. So in this case, we say that the system is approximately controllable. Now, exactly controllable in the system is exactly controllable in time t if and only if the set of restable state is exactly L2 of omega. Now, null controllability is the mean that 0 belongs to the reachable state. Then that is the three notion, the classical three notion of controllability. But here for our system, we have a heat equation. We have a heat equation that is a linear heat equation. Then null and exact controllability will be the same notion. And they will trivially imply that the system is also approximately controllable. But as we know, approximate controllability in general does not imply null or exact controllability. Now, how it is known that this null or exact controllability can be characterized in terms of an observability inequality. Then how is it known that for the interior control, the system is null or exactly controllable time t, if and only if we have this observability inequality for solution of the dual system or adjoint system or backward system that's called. Then that is the observability inequality that you can prove it, then that is equivalent that your system will be null controllable. Now for the boundary control, here we took the Dirichlet boundary control, then we also have the same, you have exactly, that the system is also exactly null controllable, if and only if you can prove this observability inequality. Here we have the Dirichlet boundary control, then it's come here the normal derivative of the solution of the backward problem. And this, you get it by doing transposition, you get that here comes the normal derivative. Now, this means that to prove null and exact controllability, one has to find some tools to prove this observability inequality. Then what is needed to prove this observability inequality? Usually in the literature, if you see that if omega is such that you know the eigenvalue and the eigenfunction of the stationary problem, this means the eigenvalue problem, if they are not explicitly or you have a gap condition, then one can usually use N-GAN type inequality and the theory of bi-orthogonal sequence. Well, that will be the case. For example, if you have an interval in R, then for Dirichlet, we know the eigenvalue, we know the eigenfunction, we know everything, then you will be able to use N-GAN type inequalities and bi-orthogonal sequences to obtain your null or exact controllability. Otherwise, the main tool used is the so-called Kahneman estimate that many people talk about that the last 2 days. Now, what about the wave equation? Then the wave equation that we have here, we also considered, just here, we consider the interior control for the wave. Then here we have the wave equation, and our control is localized in also in a non-empty open set omega. Then we want to see the reachable state here. Of course, here, if you can just start say null controllability that u of t is 0, if u of t is 0 and the velocity is not 0, then the system will not stop. Then Then to have that the system is stable, or to stabilize the system, you have that U of t, and the derivative also must be 0. Then you can have a control that both must be 0. Otherwise, your system will not stop. Then, of course, we define the three notions of controllability are the same. But here, like I said, we have to have the two components. But for the way we know that exact controllability implies null, that implies approximate controllability. Remember here that the wave is time reversible, that it may happen that null doesn't imply exact controllability. Now for the wave, how to prove the null controllability of the wave? Then usually you can take the adjoint equation, that is the adjoint wave equation. Then one can prove easily using semi-group theory that you have a unique solution, finite energy solution, and one calculate the energy. The energy is given by 1/2 that the L2 norm of the partial derivative in t plus the L2 norm of the gradient. And it's nowadays known that the energy is conserved in time. Then using the energy, because it's conserved in time, one tries to establish the following boundary observability inequality. If you can establish this boundary observability inequality, here what I denote by G, the boundary plus is the set where the set of all x at the boundary such that x, the scalar product with nu, the normal vector is positive. Then if one can establish this boundary observability inequality, one may be able to use this boundary observability inequality to obtain an interior observability inequality. Now, if you prove the interior observability inequality, then how the consequences, you will get null controllability of the wave equation in time, in positive time. Now, how to prove this observability inequality for the wave? Usually one can use the Hilbert uniqueness method that was established by Jules Lens, by Lyons in his books. One other tool than what we use is the so-called Popozaev identity. The Popozaev identity, let it here that if you take F in L2 and U is H1, 0 is a solution, a weak solution of the Dirichlet problem, then one has this identity. That is, you have a multiplier here, delta UX, gradient U, and you get this identity. Of course, this identity was established by Popozaev not to study control problem, it was to study the elliptic problem when F is when F depends on U, exactly when F of U is U power P. That's what was the main purpose for Popozaev for this identity and help him to find the optimal P where you have solution and everything. Then later, several other applications of the Popozaev identity is misprint of this Popozaev identity have been found in control theory. In summary, for the classical one, to study the controllability for the heat equation, the main tool are Ingham type inequality, bi-orthogonal sequence, and Kaliman inequality. For the wave, we have Hilbert uniqueness method, or the method of multipliers, and also micro-local analysis. Those are the main tools used to study the controllability of the classical heat and wave equation. Now let's go what we call the non-local model. What is really a non-local PDE? That what we have a non-local PDE that we know is a differential equation that may involve integral terms or pseudo-differential operator of fractional order. What we will use here for us, we will take those pseudo-differential operator of fractional order that are particular case of non-local operator. But usually what they model, those are typical model anomalies phenomena like transport or diffusions. For example, if you go in elasticity, The Pieris-Navarro's equation arrived in the description of phenomena of dislocation dynamic in crystals. Also in material science, non-local model take into account that the trace in a point may depend on the strength in a neighborhood point. That is this non-locality. Also in population dynamic, non-local reaction diffusion equation are models that analyze the interplay between food dependent growth and size dependent mortality in predator-prey system. Then we have a lot of other applications like in image processing, laser design, polar media flows, and all. Now it's there are many literature on the application of these fractional or non-local PDEs. Then the typical fractional operator that we're going to take is the fractional Laplace operator. How is defined? Then you give a real number between 0 and 1. The fractional Laplace operator can be defined as the pseudo-differential operator with symbol modulus of psi power 2s. Then it means it's an operator on order 2s. Then minus delta S of U is defined, that is a constant, a normalization constant, the inverse Fourier transform, then here times the symbol and the Fourier transform of U. Then that is what it can be defined by using Fourier transform. But another way for defining the fractional Laplacian is using singular integral. That is more common. Well, how you do? By using singular integral, we define first this space that I call LS is the measurable function such that this integral is finite. Because I want to make an integral where I have a singularity at 0, then usually we take the principal value. What we do, we integrate far from 0. That's what we call minus delta S epsilon. Then we integrate far from 0. And we take the limit when epsilon goes to 0. Then whenever this limit exists for almost every x, then what we get is say that is the fractional Laplace operator. And one can prove that if the limit exists, it will coincide with the definition of given by using the Fourier transform. There is another way for defining that, the so-called the Caffarelli-Silvestre extension, that you take it and you take an elliptic equation now on omega times 0 on the cylinder, then you get a degenerate elliptic equation, and then you solve and you take the limit when t goes to 0. You will also get another definition of the fractional Laplace, and that is called the Caffarelli-Silvestre extension. Now, our control problem that we want to study here, that here we have the heat equation, but now with the fractional Laplace operator, we have our control that is localized in a non-empty subset of omega. But now for the boundary, unfortunately, we don't have boundary, we have exterior control. Then you have the heat equation, but here our control G is localized on a non-empty open set O that is outside the domain omega where we are solving the PDE. Why this? Here you see that boundary control is replaced with exterior control. In fact, this follows from the fact that if you take, for example, you take the elliptic equation, minus delta F, S of U is F, and U is G at the boundary, this problem is not well posed. There's no solution. In order to solve this problem, the function G must be known outside omega. Then the well-posed Dirichlet problem for the fractional Laplacian is that the function must be known outside omega. That is for this reason that we do not have boundary control, but we have exterior control. Now also here, we have the same characterization for null and exact controllability. Then the system is also null and exactly controllable in time t, even only if we have this observability inequality, where also here V is the solution of the dual system. That is exactly the same because this one doesn't depend from the fractional Laplacian. Depend only if you have an operator, self-adjoint operator, I think you can get all these characterizations does not depend from the fractional Laplace. But now for the exterior control, we also have the similarity here that the system is null or exactly controllable if and only if we have here also this observability inequality. Here we have like the normal derivative, but here this normal derivative is also a non-local operator that is defined what we have here. Then it is defined like the fractional Laplace operator, but here you integrate on omega and you take x to be outside omega. That's how you define the non-local normal derivative. Then here also, to prove the null controllability, that is equivalent to prove the observability inequality. Well, also here, what are the tools needed? Then if we know the eigenvalues, then we'll be also able to use Ingham type inequality and bi-orthogonal sequences. Otherwise, we have to use all the classical case, the Kalman estimate. But unfortunately, there are no Kalman estimates available for the fractional Laplacian on bounded open set. It's not known. Then for this reason, let's see what happened, what is known for the fractional heat equation. In one that in any dimension, the system is approximately controllable. That is okay. But in one dimension, the system is null or exactly controllable if and only if S is between 1/2 and 1. Then this result has been proved first by Umberto and Hernandez Santa Maria, and later Umberto, myself, and Enrique, we use it to prove other type of controllability. For the exterior control, that is the same, that the system is null or exactly controllable from the exterior at any time t, if and only if S is between 1/2 and 1. That is also the work of our group. But what did we use to prove that? For the approximate controllability, that is clear, one use unique continuance and property of the dual system. But for the interior null controllability, one use the gap condition on the eigenvalue together with this property that we have, that the eigenvalue satisfies this property. And the eigenfunction, we have a lower bound of the eigenfunction with the L2 norm on the control region. And that was used to prove the interior null controllability. The same for the exterior null controllability, the gap condition, the eigenvalue, this property of the eigenvalue, and this property of the eigenfunction. But now we want to see the multi-D fractional heat equation. You know what happened in one dimension, but now what happened in dimension L. And that is the heat equation that we have there. Then let me recall here, then we know that the system is null or exactly controllable if and only if we have the observability inequality. But how we said before, there is no Kalman estimate. Then, and also we do not know how to prove this observability inequality without using Kalman estimate. Then for that reason, that we will proceed differently. What we do to do it, let's start first introduce the fractional order Sobolev spaces, that is the H of Rn, that is function L2, such that the Galliano semi-norm is finite. And you also know HS0, that is function is HS, that is 0 outside. While this space, if omega is, let's say, has a ellipsis continuous boundary and S is not 1/2, then this space is exactly the closure of test function in H1. But even if omega is C infinity and S is 1/2, if S is 1/2, this space is exactly the so-called Lyon space. Now let's consider the Dirichlet problem. The Dirichlet problem that for the fractional Laplacian minus delta S of U is F and U is 0 of the boundary. And the weak solution is defined exactly like the Laplacian. Here we have, that is the bilinear form corresponding to the fractional Laplacian, then if this bilinear form is integral of fv for any v in H0, then we have what we say the definition of a weak solution. Then one can prove that it's only lax milligram that for any f we have a weak solution. But the big problem, let's see what about the regularity here. That if you have a weak solution of the Dirichlet problem, if S is between 0 and 1/2, then U is in H2S. But if S is greater than or equal to 1/2 and less than 1, then U is in H2S minus epsilon. Well, after that, they said, we see here that, and then what happened, and if U here, we just have 2S minus epsilon. So then Enrique, myself, and Umberto, we proved in 2017, but at least any weak solution is in H2S log. Then we have only H2S log. Then this means that if we take here the Dirichlet problem, then the classical maximal elliptic regularity result does not hold if S is greater or equal to 1/2. And only one can achieve a maximal local elliptic regularity. Then that is the big problem in the analysis of our controllability problem, because we do not have enough regularity. Then one can think that maybe the Dirichlet problem know that we don't have maximal regularity. But what happened with the eigenfunction? Then we know that this operator, you define the operator with Dirichlet exterior condition, it has a compact resolvent. Now, if we take the normalized eigenfunction associated with the eigenvalue, then solution of Dirichlet problem, we have exactly the same result like the classical, like the result that we have there. Which means that we know that if S is less or equal to 1/2, the eigenfunction does not belong to H1. But if S is between 1/2 and 1, it is in H2S minus epsilon. In terms of continuity, the eigenfunctions are continuous, Holder continuous with Holder exponent S. That has been proved by Rostow and Serain in 2014. And one can prove that the eigenfunction is not in CS plus epsilon for any epsilon positive. This result has been proved by Valdinoshi and Servade in 1 dimension, and Enrique, myself, and Umberto generalize that in any dimension, that the eigenfunction does not belong to this space for any epsilon positive. Now, how are we going to prove our controllability result? We start with the adjoint wave equation. Then we consider the fractional wave equation here. Then here also we write the energy. The energy is given by 1/2 the L2 norm plus the 1/2 the gradient. What we call the gradient as is here, the bilinear form that we take here, this norm. Then that is our energy. And also like the Laplacian, the energy is conserved in time. Now, we recall this proposed identity for the fractional Laplacian that we will use. It has been proved by Rostow and Serra. He said that if F is in L infinity, F is in L infinity, and you take a weak solution of the Dirichlet problem, then we have this proposed identity. Remember that that is true for any F, but remember that we say that if S is less than 1/2, well, U is not in H1. But remember here we have a term X gradient. And this inequality is really critical to justify, especially in the case where S is between 0 and 1/2. Then from that, we consider solution of the wave equation that belong to here. We know which means in the span of the first J eigenfunction. It's infinite dimensional. Then we consider solution of the form P is a linear combination of the first G eigenfunction. Then using the proposed identity, we have been able to establish this identity involving the energy. Then, like I mentioned before, this term, each term must be justified carefully, since we know that the eigenfunction does not belong to H1 if S is less or equal to 1/2. But we can justify the estimate, the equality that we have, because we can prove that if you give me two eigenfunctions, even x gradient phi k is not in L2. If I multiply with phi j, the product is in L1. Then from the proposal identity, then why do we consider solution only in the span of finite number of eigenfunctions? Because it is only due in the fact that if you want to get an upper bound, to obtain a finite type of observability inequality for solution of the wave, one needs an upper bound of this term in terms of the energy. But that will not be possible when because S is between 0 and 1 because of the term gradient P. We cannot have this upper bound in finite time. That is for this reason that we consider a solution that belong to Hj. In this case, we will be able to have boundary observability inequality in finite time. Then from now on, that will be our observation domain, which means our control will live here, which means the neighborhood of the boundary. Then from that, we have been able to have a partial boundary observability inequality when S is between 1/4 and 1. We can prove that there is a constant dependent only in S such that the energy at 0 is bounded by this term, then C of A divided by T minus T0 for any T greater than T0. And we have explicit formula for T0 in terms of the eigenvalue. And that is the critical inequality that we need to have this boundary observability inequality. Then we use this boundary observability inequality. We have been able to have now an interior observability inequality, but remember always it's only for solution involving a finite number of Fourier modes. Then with this observability, we have been able, then we can conclude that we have here that projection of solutions here, y and yt are 0. We have null controllability for the projection. But this result, even if it's partial, is the first available result regarding the null controllability property of the wave equation. Now, our second step is to use transmutation technique. Why that? Because we want to transfer the observability inequality for the wave, for low frequency solution of the fractional wave, into observability inequality for low frequency solution of the heat equation. Well, to do that, we will use the so-called transmutation techniques that has been amply studied by Alvedoza and Enrique. What they did, they give an inversion of the so-called canal formula. In fact, what is the canal formula allow one to transform solution of a wave equation into solution of a heat equation. And in the paper, Alvedoza and Enrique, they provided the corresponding inversion formula. And that this inversion formula that will help us, that will exploit to obtain a partial null controllability result for the fractional heat equation. And that's what we get, that if S is between 0 and 1 and omega is as what we have found a neighborhood of the boundaries, and V is a solution in HS, then we have this observability inequality for the heat equation. Then like before, a consequence of this partial observability inequality is that the projection of solution is 0 omega. Now, we want to adapt, this is the last step, is to use the Lebot-Robiano strategy. Then I want to adapt the well-known iterative Lebot-Robiano strategy to obtain the full null controllability of the fractional heat equation. But we do it differently compared to the original version of Lebot-Robiano, where they started with the stronger quantitative version of the uncertainty principle for eigenfunction packets. But here, we replace it by the quantitative version of the frequency-dependent null control of the fractional heat equation. Then from that, that is my last slide, we have been able to prove this result very recently, that if omega is a bounded smooth open set and omega is a neighborhood of the boundary and S is between 1/2 and 1, then for any time t and u0, we can find the control function f such that the finite energy solution of the fractional heat equation vanish at time t. Well, the result is sharp because even in one dimension, we already know that the fractional heat is not null controllable if S is less or equal to 1/2. Then that is the result we have been able to prove. The proof is too technical, I didn't include the proof. Then thank you very much, Enrique, and feliz cumpleaños, joyeux anniversaire, and happy birthday, Enrique.
Merci, Mahamadi. Gracias.
Okay.
Thank you very much, Mahamadi, for your interesting talk. So let's pass to the questions. Question or comment, please. Okay. Okay, Rajesh, you can ask.
Thank you very much for this extremely interesting and informative talk. I was quite impressed. So, I mean, before I forget, I would like to request you for the slides of the talk. I mean, you can, yeah. But there are some questions on this. So, I mean, I'm not an expert, but I have some of curiosity. So I was looking at 3.6 in the equation, where using Poha-Saib you had meaning energy estimate or something like that, but it seemed local, and also the final results seem to say that. And at some point I'm a bit confused, because at some point you said that the control has to be from the outside of the domain, but it seems that, meaning the control can be through, meaning through you have an interior control or something like that. I mean, I'm a bit confused. So if you can
well, you have two. You can have interior control. That's not a problem, but we cannot have boundary control. The boundary control should be replaced by a control outside the domain.
Okay. And about the estimate 3.6 in this, meaning it seemed like it was a local kind of estimate, meaning, but I was looking.
We have inequality. 3.6, we have inequality that by using the propositive identity and the formula of the energy.
Yeah, but is it a local? It's a local energy?
Yes, or? No, it's the same energy for the fractional Laplace.
Okay. Okay. Fine. And one more question, if you don't mind. So, I mean, I didn't see in this approach any of the techniques which might have been could be useful from the approach of Caffarelli-Silvestri. Meaning, is there a way to approach these problems through their formulation of the?
No, because in the Caffarelli-Silvestri formulation, if you are in a boundary domain, if you use this formulation, you get the spectral fractional Laplacian. And the spectral fractional Laplacian is known because it has the same eigenfunction like the Dirichlet Laplacian. It's only the eigenvalue is power s, and over there is not a big deal. On a boundary domain, you cannot use the Caffarelli-Silvestri. Only on all Rn, then you can use Caffarelli-Silvestri. And here we cannot use Caffarelli-Silvestri.
Okay. And last question, maybe, meaning, so what spectral properties of the fractional Laplacian could be interesting to study in this context? Like,
well, up to now, on one interval, one know an asymptotic of the eigenvalue. There is no exact formula, even in an interval. You cannot have an exact formula. There is an asymptotic. But from the asymptotic, we have been able to prove that we have a gap condition. Okay, have a gap condition, and from that we use to prove the controllability in one dimension.
Thank you.
So thank you very much, Rajesh, for interesting questions. Sebastian, please.
Thank you, Anna. Thank you, Mahamadi, for your nice talk. It's a pleasure to see you again.
Thank you.
Mahamadi, do you think that the case of exterior contour for the wave equation can be replaced in this case to obtain a exterior contour for the heat equation? Assuming, I don't know, if the region of the exterior contour for the wave equation is near to the boundary, something like that?
That is not the problem. The problem, we will not have this transmutation, the transmutation techniques will not work.
Ah, okay, okay.
Yeah.
Okay. Ah, yeah. So the problem is only the transformation.
The transformation.
Yeah.
Well, transformation is one of the main tools. That's the main tool. You can do nothing.
Yeah. Perfect. Thank you.
Thank you, Sebastian. Gunther?
Yes, thank you. Mahamadi, thank you for the talk. Let me ask a question about the relation of this fractional Laplacian to the Caputo derivatives or Riemann-Liouville derivatives. Is there anything known in this direction, or is there any relation that is visible?
Well, yeah, let's take in one dimension, okay? If you take in one dimension, you can relate the fractional Laplacian with the so-called Marshall fractional derivative. Okay, is the Marshall.
Yes.
Then the Marshall is what the minus infinity Caputo minus infinity. That is in one dimension exactly the Marshall.
Okay, thank you.
Yeah.
Okay, thank you, Gunther. Axel?
Yes, was a question about the transformations. There's another transformation that is called FBI, you know it? That transform from the wave equation to a elliptic equation. Do you think this could be also a way to attack the problem?
Well, because we want to study the control of the heat equation. Then if we transform it to the
but in the case of the wave of the wave equation,
we transform the wave to the heat, then we have information on the wave, we transform it to the heat, then we recover the information from the wave to the heat. Yeah.
But there's another transformation that transforms the wave equation into an elliptic one, which is called FBI.
Yeah, but I don't know if it will be helpful here to study the controllability.
Yeah. No, I don't know. Was just that. Thank you.
Because the wave and elliptic is that because the difference you have the minus, okay? Then if you can put something, then you can, from the wave, you can get to an elliptic because it's only the minus that you have. Yeah.
Okay.
Okay. Thank you, Axel. Enrique, do you have a question or?
Yeah, so as Mahamadi said, I had the privilege of working with him for a number of years now, and yeah, I wanted to express my gratitude for the friendship and my admiration also. He now became a professor in the George Mason University in Washington, D.C. So he was courageous enough to jump again and to move from the University of Puerto Rico to the mainland, to the United States. Yeah, so it seems that also for Mahamadi, life is kind of a long trip, right? From, you know, where he was born, maybe close to Ouagadougou, which is a marvelous city, by the way, that I had the opportunity to visit precisely 20 years ago in 2001. And I never came back, but I will never forget Ouagadougou. And then the life is like a long trip from Ouagadougou to somewhere else, right? Maybe back home, but after a tour of the planet through France, Germany, Puerto Rico, now the US. So what is next then after these last results you presented? What is the next thing we should do or you are planning to do?
Well, we should see if we can remove that omega is a neighborhood of the boundary, but I don't know.
Yeah, that's challenging. Okay, yeah. So this will take Yeah, but someone
Five
said
more
the other
years.
day that it took 12 years to achieve a result. So we can give ourselves 12 more years, and
Yeah.
then maybe and maybe we can. Okay.
Yeah.
Good. Okay. Thank you again,
Well,
Mahamadi.
thank you, Enrique. Thank you,
Et à
Enrique.
bientôt. Je te verrai bientôt.
Yeah.
Amitié.
Oui, oui, très
Salut.
bien. Oui, oui.
Ciao.
Yeah.
Okay, thank you. I have just a small question, just for curiosity. You have mentioned for you are using Kahneman inequality for fractional heat equation, no?
No, we say there is no Kahneman estimate.
Okay, okay,
Yeah.
yes,
Because
okay.
there is no. That's why make the problem complicated. Then there's no Kahneman estimate. Then you have to find other tools to prove the controllability.
Okay, okay. So I not understand well understood. So I think you were using Kahneman. So okay,
No.
okay, okay. Thank you.
Mahamadi?
Yeah.
Yeah.
There was one more question in that context, meaning thanks to Anna. So I mean, it was not clear from the talk that there can be no Kahneman estimates, or there is no at present. So
there is no at present. On the boundary domain, it's not available. There is no. It's not known.
Me?
Yes. Can you hear me? Hello.
Yeah,
yes.
we hear you.
Yes, we hear you.
But but the thing that Rajay is not hearing. Do you hear Rajay?
Yes.
Yeah.
The connection is not good for him, I think, but we can hear you.
Rajay, then what I say, the Kahneman estimates are not available for the fractional Laplacian on boundary domain. They are not available. Oh, it's even gone. Okay. Yeah.
Okay, Axel?
No, it was just the previous.
Okay.
Sorry.
Okay.
You are muting, Anna.
Yes, thank you. So thank you again for your talk, and yes, and now we have a 10 minutes break now for a coffee break. No, so we start 11:40 time from Chile, and in 10 minutes.
Okay.
Okay. So see you.
Thank you, Anna, for coordinating the session.
Thank you.
Thank you. Thank you.
Thank you. Thank you very much.
Mahamadi, are you still there? Hello?
Yes, I'm here. Hello?
I'm sorry. I lost you completely because do you hear me?
I hear you, yeah. I can hear you.
Yeah, my connection seems to be unstable. So I couldn't hear what your reply, if you can repeat.
I'm saying that the Kahneman estimates are not available. It doesn't mean that it's not possible, but nobody has been able to prove it. Nobody has been able to prove it up to now.
Yeah. Okay. Thank you. It was very nice.
Thank you. Yeah. Thank you.
Yeah. So I sent you in the chat my email. So if you can just send me.
Yeah, let me see in the chat. I have. Yes. Okay. Yeah. You are in Chile.
Yeah. Yes, I'm at Chilean University, Concepcion.
Okay. La Concepcion. Okay. I already traveled many years in Chile. You know.
Yeah.
Let me. I just send the slide now.
Yeah, I met one of your collaborators. He was here in I mean,
Carlos.
I mean, other than Enrique, I mean to say Harbir.
Albir. Yes.
Yeah.
Okay. That's Sandy.
Thank you.
Okay, thank you.
Bye.
Okay, bye.